Hello and welcome to 3D printing of Luminaire prototypes. I'm Ashley Robbins and I'm the Director of Membership for the ILD. Our speaker will be doing a live Q&A during this session. Please click on the chat function at the bottom of your screen to type your questions. If you have any technical issues, please put them in the chat as well. Finally, the session will be recorded and available after the conference. Your microphones will be muted and cameras off for the duration of this session. I would like to introduce our speaker for today. Fredrik Fredriksson is team manager for the Light Bureau Oslo. Fredrik specializes in custom product development and project management in pursuit of connecting innovative technologies and lighting design more closely together through the implementation of processes. Fredrik is a member of the Norwegian Lighting Design Association and the ILD. Please take it away, Fredrik.
Then I would kindly like to thank for the introduction. My name is Fredrik. I'm a group manager design at the Light Bureau in Oslo, Norway. And I'm an associate ILD member. And today I would like to talk to you about the 3D printing of Luminaire prototypes and how we in Light Bureau use 3D printing as an integral part of our design process, from smaller elements and up to brackets up to full secondary reflector systems that we do and develop and design within our office. My starting in the scene of 3D printing started basically with a luminaire that I got out from when we sorted our luminaire storage at the office. It's a nice and filigrane linear fluorescent fixture, and when I got my hands on it, I realized that the one part of the covers of the luminaire was missing. And after I took contact with the manufacturer and was requesting this particular spare part to be sent, it turned out to be so complicated that I could not get it. And I realized that I needed to find another way to make this luminaire shine in its fine aesthetic way, how it is supposed to look like. So what I did is I started thinking and modulating, basically reverse designing this cap for the luminaire, and started modeling it in a 3D program. Started to get myself more interested and see also how to make this kind of model, how to modulate, how to then later put it into a slicer, which is a system to make 3D prints from a model up to the print. It basically writes the code that is later then used from the printer to know what it has to print, and to make my first assessments here to create this kind of end cap again. As you can see from the left side, we have the original part, the original cover, and on the right side we see different kind of tryouts and trial and error sequences in this printing process. It's a FDM printing process, the most standardized and known 3D printing that I've used here. And you see that I started vaguely with modeling it, and this way of reverse designing taught me a lot in how to define material thicknesses, how to define clips, how to define and make it fit to the original part. And in the end, I came out and managed to perfectly resemble the original part, and print this original part, again in all different colors and styles to make the luminaire fit again. After that experience, I wanted to go further in this world of 3D printing, and wanted to try out a bigger task. And I got myself the task of taking this aluminum container for coffee beans and try to design a reflector system. So my task was to find a solution to integrate the engine into this aluminum cavity in the housing, and by designing a reflector which puts this engine and holds it, and simultaneously give space for the driver and the electric wiring. So being tasked with that, I went to the drawing board and tried to create this asymmetric shaped reflector, also creating a button to fit in together with the seal and the lid to make like a comprehensive luminaire approach, as it's more like a task and an exercise to see if I can print something which fits in. And here you see basically the development of the reflector, and it consists of those of three main components: the secondary reflector system, including the cooling, the ribs for airing out. They have the cavity for the switch, and the holder for the heatsink plus the LED module. And as you can see throughout this linear process, you see that all of those parts set into the aluminium bin, plus the driver, plus the heatsink and the LED module fits into this cavity. And then also here I started. It's a trial and error. It was a trial and error proceeding where I printed, and you see that the surface was not refined. There were a lot of struggle with defining the right material quality, the right material thickness, and make it all work and bring it together to fit into this cavity. These slides show basically how everything is also wired and set up to make the first fittings and tests and get an idea about the proportion, get an idea about also the material quality. Usually, it's when you start off printing, we print in PLA, which is a plastic, a thermoplastic, which is not very heat resistant, but quite sturdy. But in particular, in this case, I realized very quickly that the non-heat resisting plastic can be quite a challenge to use. You see the first tryouts to make the fitting, and I realized very quickly that the luminaire and the elements fit into the cavity, and you see the effect. So this was a first great step, but I was still not done yet. The problem and the issue with the heating in the fixture became a real problem since after I left it on for like 10-15 minutes, the plastic began to deform. It began to warp, and I needed to think of a different holding mechanism and to place the heatsink. Plus that I needed to find a better solution how to take the warm air out of this cavity. So I went back and tried to design it better, and in the end ended up with like a different kind of holder, which is just a regular screw, which holds the heatsink in place, and have those smaller ribs, which now make sure that the luminaire is not overheating and the plastic is not warping and deforming. Plus that I also chose a different plastic materials. There are a couple of different materials available to print with the FDM technology, and I used PETG, which has temperature. It's much more heat and chemical resistant, and is much better use for this particular task. I also experimented in this first setup with lacquering and coloring with heat-resisting paints. The first mock-ups I did, and here you see a bit more linear how the development process has gone from the first module, where I was unsure yet about how to make the offsets, how to make the combination, the joints and the material thickness, up to the first alignments of to extract the heat, which in this particular case with horizontal ribs was not possible because the printing technology is based on layer structures, and this was this was not a good choice just to make a very stable and good print. Plus the warping of the lower part of the fixture set in again. And this is the third try and also one of the final outcome of this reflector type, which has vertical fins, vertical extraction of vertical elements to extract the heat, and have this now as a prototype and an exercise how to design a complete fixture with a 3D printed element. And this taught me a lot. It taught me a lot about detailing, correct detailing, about designing particular objects fitting in the cavity, and choosing right materials, right software, being better taught in how to use the slicer. Again, the slicer is the program which transfers a 3D model into G code, which is the language that the printer understands to basically transform the volume and the 3D model into a 3D print. So from those learnings that I got from modulating this kind of fixture, we applied this knowledge and into a practical project. Here you see a bird's eye perspective view on a project we're dealing with currently on the west coast of Norway. It's in Sandnes. And here we have a train station and a free bearing structure here in a very organic shape designed by the architect called Space Group here in Norway. And we were tasked to look into those grid allocated pillars where we have two open cavities in 70 and 90 centimeter offset from the roof, where we can have luminaires integrated to give indirect diffuse light down to the ground. So this is the task we were facing when entering this project. Here you get a bit better understanding of from this visual that we have grid allocated pillars, and it is already, you see in this picture that the spacing is rather far, and it's quite a complex task to make a very well soft and evenly illuminated roof structure here. We made first simulations to see how much light and how big of a lumen package is needed, how much effect is needed to create this effect on the roof structure. We looked carefully into where we could place the fixtures to create a nice diffuse illuminated roof, and it was only possible out of the 63 grid allocated positions to use between 45 and 50 pillars to fit luminaires into them, because not all pillars have electric wiring and cannot be in this case used to have luminaires. We started sketching first secondary reflector types to fit a 10 centimeter diameter hole that can house a luminaire which has this requested and required lumen package. So the prerequisite here is we wanted to make a hybrid luminaire consisting of a standardized element, a standardized IP60 minimum IP54 rated luminaire, including a secondary reflector system which is 3D printed to make a luminaire fitting into this cavity. And since we want to create the uplight effect on the roof, we have already automatically the physical weight, which the physical idea of that the luminaire itself is weighting and taking down the reflector in the cavity. So in the first place, we were looking into how to fit this reflector into this open hole and holding it in place. And very fast we realized that we needed to create a kind of rim which holds the luminaire in place. So we looked into this special secondary reflector, and we looked also into a first market available product which we could fit together with the secondary reflector to make a good symbiosis and to make a good hybrid total fixture. And as you can see here, we found an adequate luminaire with around 150 millimeters in height, which we could fit into the reflector. But the first question and the first difficulty that came along, that we have the whole pillar diameter is 200 millimeters, and we were not yet sure in which angle we need to place the luminaire. So that is why this luminaire became difficult to handle and was just already too big to place it into the cavity. Plus that we also needed to consider that the steel thickness of this of the pillar is varying massively between 6 and 16 millimeter. So we basically needed to create a secondary reflector which accommodates all those requests of different material thicknesses, is not extracting too far into the pillar cavity to allow the luminaire still to be placed and have sufficient space to also have the luminaire adjustable. We then went also to make first light simulations and tests and see where the luminaire is placed, how it has to be adjusted, and how in which direction it has to be put to create this, what you see on the right side, the more uniform ground illumination. And we found IP54 rated fixture, which we could mount easily into the secondary reflector cavity, which has an additional rim, making it also now easier for us to design and having also a standardized fixture to easily replace in terms of maintenance. Here you can see the first tryouts and the first 3D printed objects we did as a mock-up. On the right side, you basically see a cake box we have at the office, which had the perfect the diameter requested in this project of 20 centimeters, where we fitted, and we were studying and exploring a little bit on the idea of how this convex and concave shape of the box and the reflector fit together, and how we needed to design the outer rim to hold the reflector in place. We simultaneously did we make a more firm assessment on how to color the reflector. Should it be a dark light reflector? Should it be white in the inside, fitting basically the color scheme of the pillars? And how do the springs and the connectors into the cavity look like? Is it sufficient just with the weight of the fixture to hold the reflector in place, or do we need to have additional mountings on the side to push the reflector into place and hold it there for good? We made technical drawings to understand and to see where to place the driver, for the luminaires, how it can fit, and how it is also particularly for the electrician easiest to assess the project. We wanted, of course, to deliver this hybrid fixture like that, so that the electrician can just come and place the whole luminaire, the luminaire consisting of the effective standardized luminaire plus the secondary reflector, into the pillar cavity. And here you see the linear setup and the proceeding and processes we had designing this kind of reflector. From the left side, studying the shape, the convex and concave shape, to design a reflector which fits inside a round pillar. designing the rim and designing also the inner rim to hold the luminaire in place. So this was it came with a lot of adjustments and a lot of learnings how to design a secondary reflector fitting all those issues. And here you see basically the equivalent from last set, only in the physical FDM produced 3D prototypes that we then also used in different setups and tried it out. And we tried how steady and how firm the material should be to still be able to click and to be squeezed into the cavity. What kind of precision do we need to obey and need to take care of to make it work? Then, before we went out to the mock-up, we had this solution where we also where we simplified the reflector just for the simple case that we wanted to make basically the bridging part between the rim, the outer rim of the reflector, and the secondary reflector on the backside, standardize it up to 16 millimeter to fit any kind of material thickness from the pillars. And we created a little additional step on the bottom of the reflector to hold it in place. This turned out to be too difficult to fit into the cavity that we dropped this kind of design approach here. Here you can see a little bit. Here you can see the experiment with the right reflector on off. That also shows clearly by choosing white as a color for the reflector. We have higher luminance in the top part of the reflector, making the luminaire more visible at nighttime. Simultaneously, during daytime, the white reflector perfectly blends in with the color of the pillar and is almost not visible, particularly in the height between 3.50 meters and 5 meters inside of those inside of the pillars. And you see the light distribution, which gives slight light also to the bottom, but the main quantity of lighting goes into the ceiling. And we used also additional frosted glazing to make sure that the light is distributed as diffuse as possible to the ceiling. We also made sure to test it more severely in a light calculation and used the chance to get a light distribution curve from this reflector that we designed. Since it was already a 3D model, it could much more easily be implemented into this software to create a light distribution curve, and we could then later on use it as an effective fixture in our lighting design, in our lighting calculation program. In February 2020, we executed the final mock-up, and here you see on the left side a part of those pillars with 10 millimeters thickness, and how on the right side you see how the white produced reflector fits into this cavity. We since the project is located on the west coast of Norway, we found a producer for a 3D printer from the west coast as well, who is basically just 10-15 kilometers off from the project site, showing also the quality of 3D printing and the decentralized way of production. We can send the model to the producer, and he can print it and deliver it on site within 1 day. The technology we use to print this final version of the reflector is not FDM. It is called multi-jet fusion. Multi-jet fusion is a technology based upon powder and infrared light and an agent which fuses the different components together. This makes the print much more sturdy. It is very heat and chemical resistant and has a very smooth surface. exactly that what we were looking for this reflector. Here you see more pictures of the mock-up and the testing together with the entrepreneurs and the architect and the electrician. So we all came together and looked into how this luminaire, standardized luminaire, comes to site, how the secondary reflector system that is produced not far away comes to site, how those components are joined together and joined into the cavity and are installed. Additionally to that, there's going to be a silicone rim around the reflector to hold the reflector in place and also seal it. And here you see the final outcome, which was now, before we send it into final production, the project is due in the end of the year. If everything goes according to plan, it will be finished by the end of 2020. We have an even more adjusted luminaire type, which is now IP67 rated, not yet produced. So even this type of luminaire we could 3D print and check if it fits and has enough space in our secondary reflector print, and could give the go to produce those IP67 rated luminaires plus the reflectors. This is how the whole family of reflectors in this project looked at the end. We have the type 1, the type 2 reflector. The type 2 reflector is the reflector for the indirect lighting, bringing the light up into the ceiling. We have a type 1 reflector used only on very specific points in this project where we want to have a downlight component. So we use the same methodology and the same idea of placing the luminaire inside this secondary reflector system to create a downlight effect. Plus, we have a type 3, which is just a lock basically on those prefabricated steel pillars. We could not choose only one-sided opening. It always had to be opened on both sides in 70 and 90 centimeter offset from the roof. And therefore, we also created this kind of lock to put it later into those places where we don't have a fixture. And with this picture, I would like to thank you for your attention, and please feel free to come with any comments or questions, and I hope I will be able to answer it. Thank you.
Thank you, Frederick. That was a lovely presentation. We will not have any questions at this time, as we were doing a live Q&A during the session. Thank you all for joining us.